Today's lesson, section 12.1a, we'll be talking about sequences in summation notation. So a sequence is a function f whose domain is the set of natural numbers. So meaning starting with 1, 2, so kind of like counting numbers. So the terms of the sequence are the function values f1, f of 2, and so on all the way to f of n, and that continues to go through. So you can keep going past even n. We usually write a sub n instead of the function notation of f of n. So the terms in the sequence are going to be written as a sub 1, a sub 2, a sub 3, so on to a sub n, and then continuing on forever. Okay. So example 1 here wants us to find the first 5 terms and the 100th term of the sequence defined by the following formula. So a sub n equals n squared minus 4. So for this, if I'm looking for the first term, this is that 1 is my n value, so that's what I'm going to plug in for n. So that's kind of how it's like function notation, where before it was like f of 1, so the 1 is what you plug into like your variable inside, and so now we just have a different variable for that, or different notation. So 1 minus 4 gives us negative 3. Okay, a sub 2 would be 2 squared minus 4. So 4 minus 4 gets us 0. A sub 3 would be 3 squared minus 4, which is 9 minus 4, which is 5. A sub 4 would be 4 squared. So that gives me 16 minus 4, which is 12. Then a sub 5 be 5 squared minus 4, which is 25, minus 4 is 21. And now, so that's the first 5 right there. So this one is the 100th term. So the 100th term in that would be 100 squared minus 4 is going to be 10,000 minus 4. So it gives me 9,996. So I got my answers right there. Okay. So example 2, now they're kind of going backwards. So you're given the first few terms of a sequence. They want you to be able to write the nth. So meaning write the equation that represents this. Okay. Or the sequence equation. So you're going to have a sub n. And so you'll need n as your variable in there. Now, you can do it all together, or sometimes it helps to break apart each, especially with fractions, looking at just the numerator and then separately looking at the denominator, because sometimes they have different things going on. So for this one, looking at the top, you have 3, 4, 5, 6, 7, 8. So you're kind of just adding 1 every time to get to the next one. So if that's just the pattern and you start with the value, so let's say if you were to plug in 1, how would you get to 3? So if I was going to do that, so n plus 2 would get me to 3. And so if you want to check, make sure. So the second term, you plug in 2 plus 2 gives me 4. The third term, 5, so 3 plus 2 gives me 5. Okay, so then that works for each one. So I've got the numerator covered. Now I want to look at the denominator. And so it goes 2, 4, 6, 16, 32, 64, so it kind of doubles every time. So it's like a power of 2. So then you can also put at the bottom here 2 to the nth power. So if I plugged in 1 for that n, 2 to the first would be 2, 2 to the second would be 4. 2 to the third would be 8, 2 to the fourth would be 16, and so on and so forth. So here I've got my equation. So you can try a bunch of things, just make sure when you plug them in or you write your equation down, make sure you check. So plug in to see if you could match your terms to what you've written. Okay. Example 3 says they want us to find the first 5 terms of the sequence determined recursively by a sub 1 equals 4 and a sub n is equal to 2. times a sub n minus 1 plus 5. So what this is telling us is that if you have a recursive sequence, that means that it uses values or values from previous ones. Like, so if you had a first term, they give us it's 4, okay? So for the second term, we're going to use the first term to help us find the second term. That's what they mean by n minus 1. So for this one, if I do 2, okay? Now let's use the equation. So then 2 is my n. Then I would plug that in down here. So 2 minus 1 gets me 1. So it's really asking me for a sub 1, which is 4. So then I need to plug in 4 for that spot. So then 4 plus 5 is 9. So 2 times 9 is 18. Okay? So there's my second term. Third term, 2. So then it would be a sub 3 minus 1. So that would be the second term. So a sub 2 you just found was 18. So that's what you're going to plug in. So 18 plus 5. So that gets you 23. So that gets you 46 once you multiply it by 2. Okay? And then the process continues. So it's basically saying that a sub 4, you're going to have 2 times a sub 3 plus 5. And so a sub 3 was just 46. So that gets you 51 right there. So 2 times 51 is 102. And then a sub 5 needs you to use a sub 4's term. And so then that is 102 that you just found. Okay? So that gives you 107. So then when you multiply that by 2, it gets you 214. So there are your first 5 terms. So in a recursive statement, the first term is given to you, or the first few, because sometimes they use several previous ones. So maybe they'll give you the first 2 to help you find the next ones. But that's kind of how a recursive sequence looks like. Okay? Alright, the next thing is to do partial sums of a sequence. So if you have a sequence, a sub 1, a sub 2, a sub 3, all the way to a sub n and past, partial sums are when you take the first term is going to be the first sum. But then once you have 2 terms, then you can add that up, and that's the second term. And then, or the second partial sum, I should say. Then you get the third term, then add 1, 2, and 3 terms. That gets you the third partial sum. So it's like taking the number n and then adding all those terms that got you to that point, okay, all the way to the nth one, and that's the nth partial term, or partial sum, okay? So it's basically just adding partial sums, and then that becomes a sequence of partial sums once you have all those values, okay? So example 4 wants us to do kind of that. So find the first 4 partial sums and the nth partial sum of the sequence given a sub n equals 2n minus 1. So here we need to not only find the first regular terms of the sequence, we need to find the first 4 partial sums, and then from the first 4 partial sums we need to identify what formula or equation you could write to set up or to match what's happening with your partial sum. So it has its own pattern. So a sub n, or a sub 1, so 2 times 1, so that gets me 2 minus 1, which is 1. A sub 2, 4 minus 1, which is 3. Then a sub 3, 6 minus 1 should be 5. And a sub 4, so 2 times 4 minus 1 equals 8. Minus 1, which is 7. Okay, so there's your first terms. Now let's find the first partial sums. So S sub 1 would just be 1 because it's the first term. The second partial sum would be 1 plus 3, so that gets you 4. Okay? Third partial sum would be 1 plus 3 plus 5, that gets you 9. Then the fourth would be 1 plus 3 plus 5 plus 7, which is 16. Okay? So now here, those are the first 4 partial sums. Now I need to use these numbers, look at the pattern, and see if I can make a formula or function that represents the partial sums sequence. So looking at these, it looks like they're all perfect squares, actually. So if you did 1 squared, you get 1, 2 squared, you get 4, 3 squared, you get 9, 4 squared, you get 16. So it kind of follows that pattern. If you weren't sure, find the next one. I think the next one's 9. So 9 plus 16 will get you 25. And that also follows the same pattern, because 5 squared is 25. So if I just do n squared, that would also get me my sequence, because 1 squared would be the first one, 2 squared, 3 squared, 4 squared. Okay? Because those ones kind of match the numbers that you're given. Okay? Sigma notation. So here you're given a sequence of a sub 1, a sub 2, continuing on forever. And we can write a sum of the first n terms using summation notation. Now another phrase or word for summation notation is sigma notation, because this symbol, this little e, it's called sigma. Now sigma represents the sum of all things. Okay? And the things are, all things are what you're taking the sum of. So this part is what the function you're using to take the sum of. And so that 1, or whatever this number k is equal to, is the starting point. The n is the last term, so it's your ending value. So it's like the last number you plug in. So the 1 or whatever, because you could start at, like looking down here, you could start at 5. That's the first thing you plug into your function, and then you plug every number into like a sequence or a natural number as you move up to the nth one, and the n one is the last one. Okay? And then you just add all those up, all those terms. Okay? So example 5 wants us to find the following sums. So here we have from 9, we want to find the summation notation from 9 to 5 for k. So k is just a variable. So since we're starting at 5, that's the first thing I plug in. So I plug in 5, and that's the first one. Okay? Then I plug in 6. Okay? Then I plug in 7, plug in 8, and then the last one is 9, so I stop. So now I want to find the sum of these terms together. So that makes it 11 plus 15 plus 9. 11 plus 9 is 20. So 20 plus 15 gets me 35. Okay? And so that would be the sum. Now here's a little bit more complicated one. So here I'm going from 8 to 10, and I want to find the sum of all the terms for 2k plus 3. So like I said, you plug in the first one, which is 8. So 2 times 8 plus 3. That's one term. Then I plug in the next one, so 9. Then I plug in the next one, which is 10, which is the last one because that's the number up here. Okay? So those are all my terms. So now I want to find the sum. Now sometimes you have to simplify a little bit before you can do that. Okay, so 2 times 8 is 16, 2 times 9 is 18, and 2 times 10 is 20. Then add those, so I get 19 plus 21 plus 23. Okay? These two make 40, so 40 plus 23 would be 63. And that would be my answer. Okay? Now with trying to write the equations for your sequences, Just know there might be a little guessing and checking, so you just gotta kind of look at the pattern, see if you can match the pattern with the formula using your variable of n. Okay, so if you need some help with that one, that's a little tricky for the sequences anyway, because you kind of have to be able to see those patterns. Okay, have fun.